Alright, I have two more reactions to go over in Unit 5 carboxylic acids, and those two reactions are the synthesis of acid chlorides and Fischer esterification, and I think we'll have time to look at the mechanisms for both. We are up to reaction C, and let's talk about acid chlorides. To make an acid chloride, we're going to start with a carboxylic acid, and treat it with thionyl chloride, SOCl2. Sometimes you'll see base added, like pyridine, but I'll leave it out for now. An acid chloride is a carboxylic acid in which you replace the OH with a Cl. Acid chlorides are pretty reactive. And in the next unit, Unit 6, we're going to see several reactions coming from an acid chloride. This is all Unit 6. But it is one of the more important reactions of a carboxylic acid, so I put this in Unit 5. The other name for an acid chloride is acyl chloride. Acyl. Okay, I'll leave it at that. We'll talk more about the reactivity and the different reactions of acid chlorides in Unit 6, but the mechanism I do want to go over, it's a little bit different than what we've seen when you react an alcohol with SOCl2 to get the alkyl chloride. You've seen this reaction before, where I'm not going to cover that, where you go from an alcohol to a alkyl halide. Let's look at the mechanism. The mechanism starts very unusually. We're going to use this lone pair on the OH group, and we're going to form a double bond. Already, this is starting to look weird. That's going to force the pi bond to do something. Normally, you would think the pi bond would move up to the oxygen, but in this case, it is going to react with the thionyl chloride. This. Now, the other thing is, and I know that some websites show this, the chlorine leaves at this point, but in actuality, you should push up the pi bond to the oxygen up there, and you have this pretty large complex. Okay, can you predict what the result will look like based on my three mechanism arrows? We'll have an oxygen, sulfur, O minus, and I'll draw the pairs, two chlorines, and down here we have the oxygen that's been protonated. Okie dokie. Next thing. Whenever I see something like this, you have to make a decision. Either we could neutralize this, or we can bring back the pi bond and kick out one of the chlorines. In actuality, this happens almost exclusively, and we kick out the chlorine. What do we get here? We get plus a chloride ion Just double checking that all the charges are good. And now we do the attack, and we get that oxygen to be neutral. We still have the second oxygen here that needs to leave. That one right there. And let me just make sure I'm doing this correctly. We have now an yeah. And everything is neutral. Now this is where the leaving group leaves. Okay, we're gonna form a double bond. I call this internal lone pair to kick out this group. And a cascade effect is going to happen where that gets kicked out, but also this chlorine leaves. Just like with alcohols to alkyl chlorides, you make SO2 the gas, you also get the same thing here. And we're basically done. We still have to worry, oops. So that oxygen is actually this one down here, and it still has its hydrogen. And, oh, yeah, that one left to make SO2 gas. And you could represent gas with a parentheses G or an arrow going up. And yes, we do have chloride. Oh, did I forget something? It's not a methyl, that's a chlorine. Right? And then all of this leaves. Okay. Deprotonate to get it to be neutral, and you have your final acid chloride plus HCl. And that's why people like adding base to this, because it will neutralize the HCl, make a salt. So the HCl doesn't have a chance to, start doing some other things like protonating this oxygen again and then having, I don't know, maybe solvent attack that carbon. But overall, that is the mechanism. It is 1, 2, 3, 4, 5 steps. 1, 2, 3, 4 steps. That's all I want to talk about in terms of acid chlorides. Just keep in mind when we get to Unit 6 that acid chlorides are very reactive and they're very versatile, and we're going to see the types of molecules we'll get in that Unit 6. Next reaction is Fischer Esterification. Very famous reaction. Very easy reaction. You get an ester. Fischer, same, named after that scientist Emil Fischer. Same Fischer as in Fischer projections. Okay. And this is reaction 5D, esterification. We're going to make an ester. Okay. Let's have a very simple carboxylic acid. And I'll show you the ester that we're going to try to make. What's an ester? An ester is a molecule with 3 double bond oxygen and an alkoxy group. And the alkoxy group that I will use, I'll use this one. Remember what we said about alkoxy groups when we talked about acetals? We said that the alkoxy group comes from an alcohol. And the same thing here. This is an ester. The alkoxy group of the ester comes from an alcohol. So what alcohol are we going to use? You're just going to match what you see in your final product and then put an H. The alcohol you're going to use, in this case, will look like this. And it is acid-catalyzed, H2SO4 or hydrochloric acid. What else do you notice? You notice that you actually remove a molecule of water. I'm going to here put H2O. And where's that water coming from? Well, you're removing this OH and this H. Two H's and an oxygen per coupling, per ester bond formation. Let us take a look at the mechanism. It is going to be lengthy. I don't know if it's going to be 7 steps like acetal formation, but it's lengthy because we need to get this to be a good leaving group and then kick it out and replace it with this. It's acid-catalyzed. Interesting. I'm trying to debate whether to use H3O plus or not. Let's use actually, I believe they sell isopropanol with sulfuric acid and there's no water, but let's use sulfuric acid itself. Maybe there's enough of it that we actually do have H2SO4. I'm going to try to remember some equilibrium arrows. I'm not very consistent with this, but let's say that every proton transfer will have an equilibrium arrow. What are you going to protonate here? You're going to protonate this oxygen. Do I know this for a fact? No. But if we hit a roadblock, we'll just backtrack or restart it and protonate the other oxygen. Let's see what happens. We do get that anion, and we'll abbreviate it HSO4, right? And it's negative. Okay, so now what happens? We activated this C double bond oxygen. I'm not going to call it a carbonyl group because it's really a carboxyl. It starts from a carboxyl group. But we did activate this carbon for attack. And the attack is going to be your alcohol. We know this because the alkoxy group is coming from the alcohol. And this is where we're going to incorporate the alkoxy group. And what we're going to do next, it leaves us with 2 OH groups, and one of them is going to have to leave eventually. It leaves us with this alkoxy group that's still protonated. Okay, next. I didn't mention this, I don't believe, when we went over hemiacetal formation and acetal formation, but it's interesting that we converted the sp2 carbon into an sp3. We could call this maybe even a tetrahedral intermediate. But let us get rid of this hydrogen. We could use the sulfate anion, or we could just use another alcohol. We even use the carboxylic acid, but I'll use this OH alcohol. Get everything neutral, in other words. And we have this. Remember, our task is to remove one of these OH groups. The good thing is that we already have the alkoxy group. Okay, that's set already. And we did create this acid. And remember, OH is not a good leaving group, so let us protonate one of these OHs. Make it a good leaving group. But how are we going to kick out that leaving group? We have to recall what we did with acetal formation. Just going to run this. We are going to use what I call an internal lone pair to kick it out. Anything else I need to put? Neutralize that isopropanol. Let me zoom out so we can get the full mechanism on the screen. Okay, the last, or maybe second to last step, is kicking out the leaving group. I'm curious to see how many steps this is. We have, okay, so now we have this OH plus. We have our alkoxy. We kicked out water. So there is going to be a generation of water during this process. And then finally, to get a final ester, you know that we are going to deprotonate. Make sure that when you do this on an exam that you don't rush too fast and have your arrows start or end in the wrong place. You want it to be very close to the grader. And you did create another molecule of acid. Let's see what the steps this is. Ah, man. I thought it. I said I was going to make equilibrium errors for every proton transfer. I could fix it. So here's a proton transfer. Sorry about that. Another proton transfer. And note, a kick out. And then the last is a proton transfer. Fischer esterification is reversible. Fischer is reversible. We're not going to do the reverse here. We'll probably do this when we hydrolyze esters in unit 6, the next unit. But what is the number of steps? The number of steps are 1, 2, 3, 4, double check. 1, 2, 3, 4, 5, 6. Okay, so it's one step less than acetal formation. 6 steps. When we do the reverse in unit 6, you're going to see that hydrolysis, acid hydrolysis, is going to be 6 steps going in the reverse direction. Okay. Why don't we do some practice problems? Those are all the reactions I want to talk about with carboxylic acid. It's short because most textbooks talk about the derivatives of carboxylic acid in the following chapter. And I'm going to do the same thing. In a different unit, I'm going to talk about carboxylic acid derivatives. Let's practice. How do we make, oh, this is interesting. Why does this happen here? We have a carboxyl group, and I'm going to make sure I write this right. I'm going to put the OH here, actually. I am going to imply that we're doing a Fischer esterification by putting acid. But what do we realize about this Fischer esterification? That we are having our hydroxyl group and our carboxyl group in the same molecule. And if we take a look at here, remember how I put a dotted circle around the atoms that are leaving, OH and H? And what happened? That oxygen ultimately attached to the dot, right? Let's use those Q's. And we are getting rid of the OH of the carboxyl group, the H of the hydroxyl group, and our dot is right here. What am I hinting at, or what am I asking us to do? I'm asking us to draw the cyclic ester. Again, I didn't formally tell you this. An ester is, like, maybe I did actually. An ester is a molecule with a C double bond oxygen with an alkoxy group. It looks like a carboxylic acid, except you replace the H with an alkyl group. Okay. How do we make this ester, and how do we make it look clean so the grader doesn't misinterpret it? Count how many atoms are going to be in your ring. If you really think that this oxygen eventually will attach to this dot, you're closing the bracelet and you have 1, 2, 3, 4, 5. It's a 5-membered ring, and the main bond was between the dot and the O. Do that first. A 5-membered ring between the dot and the O. Then, after you have the ring set, then you start worrying about all the decoration. And the decoration is what? The decoration is that that dot, call it carbon number 1, 2, 3, 4, 5, 6, 7. There's 1, 2, 3, 4. Okay, that makes sense. 4 has the oxygen. 4 has the oxygen. 5, 6, and 7 are off of the ring. 5, 6, 7. 5, 6, 7. Keep in mind that we are making a now cyclic ester. And what is an ester? It's a molecule with a C double bond oxygen with an OR group. Well, where would the C double bond oxygen be? If we take a look at our plate, it stays exactly where it was in the starter material with the dots, right? Just put where you know the oxygen goes. Honestly, I'm not thinking about the mechanism. Normally, I would be thinking about the mechanism to figure out, what's going to happen with this group. But I know that I'm making an ester, and that's the only place it makes sense. The dot. Now, a cyclic ester has a fancy name. It's called a lactone. I have not yet talked about the nomenclature of esters. That's future. Don't get this confused with ether. We have done a lot of ether stuff, right? Ether is, well, this could be an ether, right? It's an oxygen with a carbon, bond to carbon on each side, and nothing else. Okay, so that is how you would go about making the cyclic lactone, not cyclic lactone, the cyclic ester, which is a lactone. At home, what do you think I'm going to ask for the mechanism? Try to apply what you saw in the template and try to apply it to this. What was the first step? The way that I'm suggesting my students to learn mechanisms is to memorize the first step. It's not that bad. We have a acid. You got to protonate something. But yes, you got to memorize what it's going to protonate. In real life, if you put yourself in the round bottom flask, yeah, all of these oxygens get protonated, but they get deprotonated quickly as well. But there is one location for protonation that once that happens, then a cascade effect will occur. And that is if you protonate the oxygen with the carbon double bond. Once that occurs, then you have this attack of the nucleophile. So for the mechanism, let's verbalize it. You're going to protonate this, first step. Second step, the alkoxy groups come in, and then I'm lost. But at least I get the first 2 steps, and I could guarantee you that once you draw the product for the second step, you'll know what to do for the third step. Okay, it's like cues. The preceding product will tell you what to do moving forward. But get off to a good foot and memorize that first step. Protonation of the protonation of the oxygen of the carbon-oxygen double bond. Is there anything else I want to say about acid chlorides and esterification? No, not really. The next unit, again, we are going to be continuing to talk about acid chlorides, but also esters for synthesis, because we still have more reactions to do with these, but those are typically put in the unit of derivatives, things that come from carboxylic acids. And for my class, that's it for Unit 5. I'll see you in Unit 6.